So let me do a little bit of a recap from yesterday's lecture. So yesterday we said that infinitely wide deep neural networks at the level of their priors are Gaussian processes. We derived the recursion relationships for them, and that'll come up today when we talk about the NTK. But then we also did learning. Okay, so we didn't just talk about random networks, but we conditioned on the data set. And I kind of, at some point, I wrote down some formulas for when you do Bayesian inference just with a Gaussian process. You can get these closed form formulas for the mean predictive posterior and the variance of that. So given a training data set, you can go calculate that. So you can learn in this infinitely wide neural network in a Bayesian way. So today we're going to also compare those formulas to what you get when you do empirical risk minimization in the infinitely wide setting, and the formulas are going to have some similarities with each other. We also, at the very end, talked a little bit, or I tried to give a little bit of a taste of the what happens when you take depth to be large in these kinds of recursion relationships. So generally speaking, they become pretty degenerate because you're not passing the signal from the input back in, to the deeper layers, and so at some point it just kind of dies out. And in the interest of time, I think we're not going to revisit that topic unless we end up having more time, but just move on to other things. Okay, so left over from last lecture, so let me just say, that we did do learning with these GPs, and we got formulas for kind of the mean of the predictive distribution and a variance given some test point x star. And we'll come back to that again today. What I want to do now is just talk a little bit about finite-sized networks and not talk about it in a full level of generality. So it's, in general, difficult to write down a general prior over functions for a finite-sized neural network with all the nonlinearities. You can do it perturbatively. Maybe Boris will say a bit more about this. I want to use this as an opportunity to kind of make one point about the way moments get affected when you go to a finite-sized network, and then also use it really as an opportunity to introduce a technique that, or like a computational technique that I think the physicists know, but maybe others are less familiar with or know in a different form, which is Wick's theorem. So how many of you know Wick's theorem? Okay, many people. Well, let's just use it for a couple of calculations. Then I guess nobody needs to see the derivation of Wick's theorem, or how many people would like to see that? Nobody needs to see. Okay, so then let me just state what Wick's theorem is and then tell you how to get it. So suppose I have question. Z is some n-dimensional random variable which has a multivariate normal distribution with a covariance function k. Then if I want to compute an expectation like this, where I take, 2m numbers of z's, the different, I have 2m different coordinates, and I want to compute the expectation over the distribution, there's this result, which is that I can get that by just taking the elements of the covariance matrix on these on this n-dimensional space, indexing into that, and taking all possible pairings of the variables here. So these are now kind of assignments of these variables that I have here in all the possible orders that I can have to the other side. And that's what this sum is supposed to represent. So to derive something like this, you can start by going back to things like a partition function, for a Gaussian distribution with a source, J. So this, how many of you are very familiar with this sort of thing? So something like if I compute this expectation value against the distribution of the z's, this is a generating function for moments because I can differentiate the j's, which are the sources, however many times I want to generate more z's. And now for the Gaussian distribution, you can actually compute this partition function with the source exactly. And then you generate moments by taking derivatives with respect to j's. I'm going to take some number of derivatives here, and what ends up happening is that these k's kind of come out. So let me just write the answer for what this is for a Gaussian. Up to some normalization. Let me just ignore the other constants out in front. And then you differentiate this with respect to the j's. It'll generate k's. When you set j equal to 0, then you've calculated the moments. So and then afterwards, set j equal to 0. And that's how you get this equation. So physicists use this a lot because it's a nice, just kind of combinatorial way to keep track of these moments and just map it onto pairings of different indices of these variables.
In the statement of theorem, what is the between variance k, mu, k,
2m minus 1. Yeah. Sorry about that. Okay. So with that, what we're going to do is just calculate some of these moments for a deep linear network. And we're going to derive some recursion relationships now, not just between the second moments, which is what we did yesterday, basically. That was the covariance function, but between the higher moments. Let me remind you kind of this the two-point correlation, which at the infinite width level is just the kernel matrix or covariance function we wrote down yesterday. So suppose I want to calculate something like this. Okay, and I have a neural network. It's going to be linear. Let me drop the biases also for simplicity. So this is the type of thing we had yesterday, right? Except that we were working in the infinite width limit. Now, for this case, I'm going to use the property of my prior that I have, which is that these indices have to be the same. I get this 1 over n again, remember, from the prior. And so this, let me define because this delta I1, I2 is always going to be here, because it comes from basically the Kronecker delta function constraint on the leading index of the W's. Let me factor that out, because I don't want to keep track of the index structure of these things. Let me just define this to be delta 1 I2 times this part, which is not keeping track of the index structure on the hidden nodes, but just tracks the layer index, and here also has samples in it. Right now we just have 2 samples, alpha and beta. So let me define, use this to define the G's, where another way of saying that is that the G's are this thing kind of with the constants in here. Okay, so this gives us a recursion relationship where this G from layer L to layer L plus 1 just get multiplied by a constant. So this is really, again, keeping track of just the 2-point correlation function for 2 different samples. In the infinite width limit, it's just the K's from yesterday. Okay, so note that if this thing is larger than 1, then this blows up with depth. If it's smaller than 1, it shrinks, and so on. Okay. So if you, let me just put it back. Take it from the initial layer out to layer L, you have something like this. Okay, so now for the higher moments, excuse me, let me just drop the sample dependence and just study the single sample case just to keep track of fewer things. So you can, of course, generalize this to however many samples you want. And Boris will do this, I think, in a different way, using a different technique in more generality later on. But let's calculate the 4-point version of this, dropping the samples. So now we just have, we want to calculate kind of the expectation of 4 of these Z's. Different hidden nodes, same sample. What is, how correlated are they? So you don't have to write all this down, just maybe watch what happens with the indices and the calculations. So now we're going to apply Wick's theorem. Note that we're applying Wick's theorem to just the weight matrices, not the pre-activations, which are not Gaussian, but we're using it just on the weights. And so here we use Wick's theorem. The covariance matrix for this is the identity, so we're just going to get Kronecker deltas out of this, and we're going to have to look at all the possible pairings of these indices. So it'll be things like delta I1, I2, delta I3, I4, plus delta I1, I3, I2, I4, plus one more pairing. And then there are some delta J's, but let me just kind of Kronecker deltas on the J's, but let me just impose that already in a sum. So I've kind of done some of the sums on these other variables. And there's an n squared from, two factors of the variance. Okay, so this index structure is kind of similar to that other one. Let's again try to just factor it out so we don't track it in the recursions. So let me define kind of expectation of something with this sort of structure as just this sum of Kroneckers times G4L. So this, from now on, these G sub something is going to tell me which moment I'm calculating. So this is like the fourth moment. I'm going to relabel those to G2, and it's at the Lth layer. So with this, we get some relationship between G4 at L+1 and G4 at layer L. And there are factors of width and so on in that. So if you plug in knowledge of this index structure kind of into here, let me maybe skip writing all of those steps and just tell you basically what the answer ends up being. So here, when you plug in knowledge of this index structure into here, what you're going to have are things like delta jj, delta kk, plus delta jk, delta jk, plus the same thing. Okay, so that, if you imagine then, when you do, there's a sum here over j and k. When you do the sum, we'll give different factors of n and so on. And the final answer, let me just write it. Is something like this. So there's a correction here that's coming from the finite width aspect of it. If you set that to 0, it's completely uncorrected. Say that again?
So in the calculations, this thing comes out, but the 2 over n, I guess, it corresponds to the delta jk paths, right?
That's right.
So that is not there defined. Okay.
That's right. That's right, yeah.
Are we allowing 4 different inputs here, or are they all the same?
This is all the same input, just for simplicity. Otherwise, you have more indices to track. So in general, then this would be a function of, 4 samples also, as well as the hidden node structure. So that's just a bit more work for us. Let me do this thing where I write it now. I repeat this all the way till I get to G4 at layer 0, and then I relate layer 0 to I relate the fourth moment to the second moments at layer 0. And at that point, we know what the answer is because everything is Gaussian. Those first initial preactivations are just Gaussian, and there are no corrections. So when you push it all the way back at every layer, you pick up one of these factors. You pick up also this to the Lth power. And then there's a relation between G40 and G20. And so I've written it that way. But if you now push it forward again via the relationship between the second moments at layer 0 and layer L, another way of writing this is like this. So what it says is that the relationship between, let me write this, actually this is now G4 at layer L. We have equations that look like this, which tell us that if we want to look at the fourth moment at layer L, you know, it's related to the second moment at layer L. You know, if the variables were completely Gaussian, so if these pre-activations could stay completely Gaussian, we know the fourth moments are completely determined by the second moments, just as related by the square. But we pick up some correction factor through all the layers that we've propagated forward. So there's both the finite with correction, but it's getting kind of multiplied in with every depth. And that's kind of one of the takeaways I wanted to make from this calculation. You can continue this again for like G6 of L, and so on. It's a tedious calculation, but basically if you take, you know, rephrasing what I stated here, if you take this difference, which is the difference between, you know, the fourth moment and the second moment squared, which would be 0 if they were Gaussian, if the activations were Gaussian, plug this in and do kind of extract the leading order term. You get something like this. So the amount of non-Gaussianity you have, this is some kind of heuristic measure of that, depends on depth over width. There's a correction at every width, and then it's getting amplified. So reference for this, if you want to read more, is this manuscript. I think Boris will talk a bit more about this in full generality, but one of the things I wanted to mention was just having Wick's theorem kind of at the back of your hand to estimate correlation functions, and we'll use that again in lecture 3 to do some kind of perturbation theory for calculating corrections to the kernel. Any questions about this? Okay. L prime equal 1 to L minus 1.
And the L prime appear in the product, in the actual formula?
No.
Okay.
I guess it's just this.
That part also does not depend on the prime.
Yeah, it's just this to the nth power, basically. I believe is the correct example of that. Okay, so let me now move away from random networks, Bayesian inference, and so on, and we're going to talk about dynamics in the infinite width limit under gradient descent and empirical risk minimization, and talk a little bit about the NTK results, and maybe just clarify a few kind of things that I often hear, or maybe misconceptions at times about it. So let's think about dynamics in function space. So we're going to be running, gradient descent. It'll be full batch. We'll also talk about gradient flow. And let me just note that if you want to track the evolution of the function that arises from doing this, sometimes I'm going to write this as either ft of x, but then remember that all of the t dependence just comes from the parameters. So sometimes I'll also kind of think about it as some parametric model, and all of the t dependence is coming from here. So I want to plug this into this. So this is really, let me turn it into vectors. I apologize, I'm going to sometimes go between vectors and also just like indices that are going to be summed over and contracted quite a lot. So to really understand the full kind of discrete time function evolution, you're going to have to Taylor expand. One way of doing it is to Taylor expand this dependence here. So there will be kind of in this lecture and the next a lot of these like derivatives written out with indices and contractions. I hope that's okay. It's a bit tedious. Physicists tend to do it a lot, but it's sometimes helpful, I think, at least for me, to see things written out. So in principle, you would need all of these things. This first term is the thing that gives you in continuous time something that you know, which is if I do now the continuous time version of this, what we're going to do is basically always today and tomorrow is try to separate out the kind of the time dependence that comes from the relationship between the function and the loss, which for us will often be square loss, so it's just controlled by a residual term, and the relationship between the function and the parameters. So we're always going to like factor that loss dl df part out, and then push all the derivatives of the function into some object. So if I write this out, one way of writing this is just like this via chain rule, where I do this. This is for the case of full batch gradient descent. So you can generalize it, to the stochastic case if you like. But sorry. This is just a change of variables, and we're going to keep doing this sort of change. And another type of derivative substitution that we're going to keep doing is when I have something like d dt, I'm going to write it as something like this, because all of the time dependence just comes from the parameters. So this helps me apply derivatives to objects like the functions, and here I'm going to substitute, the update from gradient flow or gradient descent as well. Okay, so coming back to this, I'm going to substitute for this. You see what comes out. I'm going to factor out kind of this residual piece, which is something like this. And then all the kind of function and parameter relationships are going to be in this other object. And eta equals, eta is meaningless in continuous time, so let me just drop it. But this, is probably an equation you're used to from NTK. So now I'm going to define this thing. It's a big theta, as to differentiate it with my little thetas, which are the parameters. I'm just going to take this as the definition of some dynamical variable. So this is a setup kind of for how NTK kind of goes, but I'm doing it a little bit more, keeping the time dependence, because tomorrow we're gonna like study this as a dynamical variable. Any questions about this so far? How many have seen this? But note also that if you go to discrete time, there are other things that govern, in principle could affect your function evolution that you might need to worry about. And so for us, we're going to be doing square loss, so often this will look like something like this. And I'll refer to this as the residual piece. Okay, just to illustrate how you can keep pushing this forward and give you a sense of the sum equation we'll look at tomorrow. Let me actually do what I said, which is every time I have a DDT, I'm going to make the substitution. So I'm going to take DDT of this NTK as a dynamical variable. So there's a piece that looks like this, and then the piece that comes from just exchanging x and x prime. And now we substitute into here with this thing. So this is going to give us an extra derivative acting on this. So we'll give us a second derivative. Then we're going to substitute in with the dynamics from gradient flow for the parameters. And so I'm going to skip one step of doing that and write the final answer. Hopefully it's okay. Okay, so notice that, first of all the parameter dependence kind of derivatives with respect to parameters have been pushed into this thing in the brackets. We're summing over all of them in the network. Right now, nothing is infinite size, so we're just summing mu from 1 to p. There are 3 samples coming in here. So there's an evaluation, and let me not repeat that, but x and x prime are arbitrary arguments, and then there's just one thing that we're summing over, which is this index alpha, which runs over the data set, but this is an arbitrary function of x and x prime. And again, this part is like this. Okay, so where am I going with this? What we're going to do is look at these equations later on. So like in NTK, what happens is that this thing, at initialization is, if you estimate it at initialization, it vanishes with the width. And that remains through during the course of training. Okay, but if that's kind of, if you want to now start understanding what happens as you move away from, infinite width, this sort of thing starts to play some small role. It's a small correction, and you're going to try to track it. So when I refer to NTK, think of it, probably a lot of you already do this, but there's what that might, what that meant in the original paper was kind of the deterministic limiting kind of kernel object that you get at infinite width, which you could evaluate at initialization, and then just take the width to be infinity. And then there's the other thing, which is it as a dynamical variable, whose dynamics you want to study. Any questions about this so far? No. Okay. I guess how familiar is everyone with, say, computing NTKs for different types of networks and kind of writing down or looking at expressions for DDT? Lots of people? How many would like to see it? Okay. Let me just take 1 second to do one example, which is just a single hidden layer network. So this is an NTK parameterization where I explicitly factored out a root n. I'll come back to like different parameterizations in a little bit. But if you write down, what NTK is at finite width, the derivatives with respect to the W1s give you something like this, summed over I. The derivatives now with respect to the first layer variables give rise to something like this. Okay, so note that everything here is an order 1 quantity. So this thing is, order 1 doesn't matter, it has no independence. This thing is summing over, n random things with a 1 over n. And likewise here. Okay, so,
Is now derivative
derivative with respect to
the bias of the first layer.
Did I?
No,
I might have dropped that. I think I dropped that. Yeah, you're right. So this is something that is order 1. I'm waving my hands now, so this is where mathematically you should make it more precise, but I'm going to be more like a physicist. So it's something that's order 1. It's random at finite width, but it's going to converge, as Jaco et al. Proved, to some deterministic limit, and it's not going to fluctuate at infinite width. And these look very similar kind of to the sorts of expressions we wrote down yesterday. I don't know if you remember, but this is kind of like the kernel from the NNGP that we talked about yesterday, and this is like everything from earlier on. So this is, in general, these are like t dependent. So that's implicit. Yeah, there's no t, but if I wanted to calculate it at some particular time, I could. So order 1 quantity, and Okay, similar to that more general thing we wrote there, but let's just see how it comes out. If I take a time derivative here, okay, I'm going to get a whole bunch of expressions. It's kind of ugly. But I'm going to take derivatives kind of with respect to time derivatives from the z sub zeros and time derivatives from the w1s. And each of those are going to be suppressed by some factor. So let me write that. So you have something like the pre-activations coming into the first layer. This is all just stuff, but what's important is just that there's a 1 over root n here, and everything else is order 1, and the sum is not n-dependent. So this kind of just as an estimate of scales is something that, you know, it's order 1 over root n. Now I'm being a little bit sloppy by whether I should estimate like means or variances and so on and treat this as random variables, but just want to give you a sense of the scale. So these scales, this is suppressed. You see it come out explicitly because of this NTK parameterization. And then similarly, if you write down, you know, the evolution equation for d1i for the last layer weights, you know, this is, again, this, let me call this a residual, or sub alpha. This is going to be phi of so again, 1 over n suppressed. So then plugging in for the time derivative of theta, those things are going to be 1 over n, you know, 1 over root n suppressed, and none of the sums are going to change. You're still summing over the same number. So that's where the suppression in d theta dt comes from if you estimate everything at initialization. So far we've kind of just been plugging in, you know, the fact that when I initialize, these things are all order 1. The residual is something that's order 1. And so the rough idea is that, you know, if these things are suppressed, if I take some finite number order 1 steps, they're still suppressed because I kind of just sum up, you know, 1 over root n some constant number of times. But now what I really need to do is show that you know, this stays true throughout all of training. It's the more non-trivial part. And what ends up helping you is the fact that the loss is decreasing quite rapidly at the same time. And in particular with these square losses, you know, you're going to get kind of, there's an exponential in time decay to 0. It converges at a linear rate. And so, you know, you're not really summing 1 over root n infinitely many times, but there's a e to the minus t that's helping you. So that makes the final kind of correction, the ultimate change over the course of training small. So that's kind of the intuition for what happens. Now this was all kind of presented in function space, sort of, which is how I think kind of like the original, kind of schematically, the original proof goes. It's a bit cleaner to kind of also, I think, do it in parameter space, where you kind of Taylor expand the model and show an equivalence to a linear model. Okay, any questions about this? How many people have seen this, feel super familiar with this? Okay. Let me just take this time to derive the NTK recursion relationships for the kernels, given that we spent some time on the NNGP kernel yesterday. Also because what's kind of used implicitly in there is the fact that these intermediate hidden layers are Gaussian processes with particular kernel functions that we derived. So you'll see that kind of arise in this nested form. Okay, a lot of this, as you know, is from logical. Okay, they have a theorem showing that the NTK as width approaches infinity approaches this deterministic limit, and let's derive a recursion relationship for that. So. To do this, let me. Okay, I didn't state the theorem, but. To derive the recursion now, kind of assuming their theorem is true and the intermediate parts, let me divide let me kind of do it by induction. So I want to separate out the parameters in the last layer with all the parameters that come from the earlier layers. And I take the derivatives of the function with respect to parameters. So let me say I want to calculate the NTK at layer L for outputs k and j of the function. I'm going to eventually drop this because it's going to be diagonal in these indices, so we'll eliminate them later. So this is, let me divide this into the last layer derivatives. Let me just, to save myself from writing all this. Where I have the inner product over the gradients as well from all the earlier layers. Now, this is the form of the recursion that I'm going to use. What I've done is just put explicitly these sigma b and sigma w factors back in just to make it look like something you derived yesterday. But it's not super important. It's just whether I want to explicitly, these are like came from constants in the prior. I can choose whether I want to pull them out as NTK does or put them elsewhere. Okay, let's now just plug in for these derivatives. So the first piece is going to be a derivative with respect to the b's, and then a derivative with respect to this final layer weight matrix. So there's going to be a term delta kj sigma squared b. Also a delta kj from the weight matrix derivative. Okay, so something like this for just the derivatives with respect to the last layer, right? So this looks, as you can see, it's starting to look a lot like the kernel we got yesterday. And then we have derivatives from all the other layers. That requires me to take derivatives through the nonlinearity. And then I just need derivatives of the ZL minus 1s with respect to parameters, but that's like the NTK at the earlier layer. You know, at finite width. So what happens as width increases is that by the law of large numbers, this thing is kind of approaching something deterministic, which we can write down as an expectation over these different random variables. Now we need to know something about the z's. The z's are Gaussian, are distributed by this GP that we derived yesterday. So we're going to use knowledge of that to calculate this. And then similarly here, these z's are governed by the GP, and this approaches that kernel that we also derived yesterday. So let me just derive, reminder there was this function from yesterday, which is a function of a 2x2 kernel matrix, where if you give me the kernel matrix, I give you some value that comes from calculating this two-dimensional integral. So really it comes from computing this expectation where u and v are normal with covariance sigma. This was just from yesterday, and what I was doing was plugging in the k's in here. There was a 2x2 matrix, and it really just depended on 3 of the matrix elements. Okay, there's an analogous function that comes with a tilde. All right, let me just label it with a tilde, which is the expectation of these derivatives with the same condition. And that's what we're going to use here. So this first term, let me just write out the final answer. There's some Kronecker delta out in front. This thing is KL xx prime, because this looks like sigma squared b plus the stuff times this f function from yesterday, where these are Gaussian distributed, and then what we have is sigma squared w. This other function, f tilde, which involves these derivatives, which is a function of KL minus 1, because it comes from these GPs from the earlier layer, times this thing. Okay, so you see that the way we're here, I've dropped KJ, assuming kind of that it's just the diagonal piece that we're tracking. So you see the way that the NNGP kind of covariances come in some kind of strange way. Sometimes it's just added in. That's because this is just coming from the derivative with respect to the last layer. And then it's coming in also in this nested way into these derivative computations.
Can you say something about the relative
Strength?
magnitude of the two terms typically?
I don't know them to be different in strength that much, to my knowledge. Yeah, nothing comes to mind, I guess, for typical choices of like sigma W and sigma B. Yeah, I don't remember, actually, if one dominates the other. One way that they are different is just, and this difference tends to matter, I think, more when you're doing finite width kernel calculations or random features, is that the theta is really a sum over many more random variables, because it's a sum over many layers. So that kind of averages a bit faster because you're summing over more things. Whereas this kernel K is just the last layer kernel. So if you have a network of a certain size of a certain width, the NNGP is going to be, if you're working kind of in the random features limit, you're only summing over, O of n things from the last layer width, as opposed to like n times depth things from all the earlier layers. So it has that sort of, that's one place where it matters.
I think to Kamesh's question, if you sort of have a typical initialization, then as you get deeper, as L increases, then the KL sort of stays around the same size, but theta of L can get bigger and bigger. So sort of like the deeper you go, the bigger and the NK is relative to the NNGP, but it'll never like totally go in.
I mean, maybe you can think about it as just that if you initialize well, that free factor in front of theta should be very close to 1. Otherwise, you get exponential blow up over k, and then KL just the source term for theta. And as you're saying, like, if KL is order 1, theta should be order L. I mean, it's summing up over L k's. And so theta will typically be bigger, as you guys are saying. But that's kind of the relationship between the two of this recursion.
Okay, thanks for that. Any?
So we can see that. Is this enough to see that sort of if you only tune the last layer, then the two kernels are the same?
Yeah. So like if if you only train the last layer, then you just need the relevant kernel for that dynamics is just the last layer kind of derivatives. So it's just this, and then you wouldn't have these derivatives appearing. And then you could kind of track that. That's right. Thanks. How much time do I have? What is this?
Half an hour.
Half an hour. Okay. So in that case, let me now just, before I talk a bit about the intermediate steps of some proof, talk about the consequences, which also you might be pretty familiar with, but let me repeat some of them. So in this continuous time formulation, you can solve for the function and both the parameters exactly. This is something that everybody knows. You can integrate these equations and get terms that depend on exponentials of theta t. So is it worthwhile to write this, or this is something that you all raise your hand if you would like to see me write this? Okay. Sorry for being a bit repetitive. So let's just go back to this thing. Okay, so this is one thing that you can solve for the function, and you can also solve the linearized version of it, where you do a first order Taylor expansion. If you do that in continuous time, you get something like this. So let me kind of write it in this sort of block form where this big X, or something that kind of looks like a chi, is really a matrix constructed by evaluating these gradients on all the different data points. So it's something that's like a number of parameters by amount of data. This theta, all these theta knots are also evaluated on the data. In this case of full batch, where we have the same, the full data set coming in every time, we have something like this. And keep in mind that per coordinate, each one of these gradients is small in this NTK parameterization. So like there's a 1 over root n or something of that form in front of each one of these terms. So per parameter, the total change is small. But then when you sum over all the entire parameter vector, it's something that's order 1, it's different. Okay, you can write down the solution at any arbitrary x into two terms. So what are these two terms? Why are they separated out? So this is a single point x. So the solution looks something like this. Okay, so what I mean by this is if I don't write explicitly the arguments, I mean that it's evaluated on the data set, which is like m by m, if m is the number of samples. When I write out explicitly the arguments, that means that I evaluate it here on the test point against kind of the entire data set. So this is now just a vector that gives me the value of mu at a particular data point. And this gamma is something that looks like this. So I've grouped here all the terms that depend on the initial value of the function. So now what I'm doing is I'm taking a very large model, really in the limit, and there's some randomness coming just from the initialization, which I haven't summed over yet. It's just a fixed initialization, and I'm running kind of the dynamics forward. So this is the value of the function at initialization on x. This is the value on all the training data points. And so I wrote it in this form so that now we can kind of think about the distributional nature of this if we average, the randomness here comes from the randomness at initialization, which we studied yesterday, which is this GP kind of property. And so these, this is like a sample from the GP. This is also a sample from the GP. So these are all Gaussian distributed. And we're just multiplying in some of these constants. It's like an affine transformation of these f-zeros. And so it's going to stay Gaussian distributed. And so the final distribution for any, let me write it like this. I'm going to write this. Let me take a batch of test points chi t. There's going to be mu of chi t, which is just evaluating on that batch. There's no randomness coming from that term. And then there's this variance. So to avoid writing more exponentials as a function of time, let me just take the t going to infinity limit of this thing. So that just gives me a y over here. You can plug that back in if you like, but if I run it to infinity, okay, I'm going to write out a somewhat long expression, but I just want us to stare at it for a little bit. what's going on here? So I've tried to make explicit where you evaluate on the test points. So that's all the chi-t's that you see. But everything else that I didn't write is just evaluated on the training data. So this is some, okay, involved product of theta inverse k, theta inverse, theta naught, and likewise here, and Hermitian conjugate here really just means transpose. These are all positive. And the reason I wanted to write this was, okay, so the final distribution is something that looks like, you know, normal with mean mu and covariance sigma. And I wanted us to compare this to the answer you get from Bayesian inference, right? So that answer, I actually, okay, I won't write it out. Do you remember it from yesterday? It's more of, it's k inverse y, so which collapses to the same thing here. And here it was going to be something like, so that's, sorry for a lot of terms, but those are just the two expressions you want to compare. So this actually, if you plug in, you know, theta naught equal to k, this should recover that expression. And indeed it does. Okay. That's a sanity check. But yeah, this is kind of the predictive GP you get with ERM and gradient descent.
Sorry, what is the distinction between K and theta 0?
K at
Theta 0, the kernel at initialization.
so my K and K naught, the K, theta 0 is the NTK at initialization. K is the kernels from yesterday, which is theta naught if I just differentiate with respect to the last layer. So K, so I have two functions. One is this one. One is this one. I could drop the naught. You know, if you like, it's just, it's the infinite width limit at initialization of NTK. These are in general different. If I, you know, if I differentiate, if I had derivatives with respect to all the earlier layers as well. So the final distribution, when you take into account the randomness from initialization, because that's what's affecting F naught, you know, that randomness was governed by this covariance K, and that's why it follows through in the distribution. So if you set F0, if you set it to 0 initially, then you don't have to worry about this, and you just have kind of that same term.
So sorry, I'm also kind of confused about that. So I remember that from yesterday. But how do we conclude it's the same thing? We conclude that theta 0 is equal to k, or?
That's a special case. We didn't do that. We don't want to do that in general. This is the general formula.
So can you repeat what we conclude about the comparison?
Just that they look different in the general case of ERM and gradient descent. They involve, you know, here I'm using, you know, the NTK kernel. There I'm just using like the last layer covariance matrix kernel. The variances are a bit different, but they kind of collapse to one another if you set k to theta. In the special case where you're kind of training just the last layer. But they were two different kind of, you know, algorithms that we were running.
So you're saying if theta 0 was equal to k, then it is the same thing?
Yeah, the form from this point of view. Yeah. in this like distributional sense, the formulas come out the same. Like k is equal to theta, so these sorts of things cancel. Anyway, so both of them give you GPs at the level of distributions. They give you different GPs, and this one is not doing anything Bayesian in the background. And this was also running time to infinity. So, at finite time, the expressions are different. You still have these exponentials hanging around.
Yes,
Mhm.
they can make a comment about the comparison between them. The prior is always the same in function space. We still use the NNGP. That's how we initialize. But it's like you change the inner product for doing your optimization. You don't compare inner product with respect to k, but rather with respect to theta. So like in the likelihood, you're measuring the norm in the RKHS corresponding to theta.
Mm-hmm.
And it's like doing gradient descent with a different inner product, and that's why the thetas get interleaved.
Yeah,
And
that's
if theta
really
and k were
nice.
the same, then you get the answer you got before, but it's a slightly different RKHS in which you're doing your optimization or your calculations.
Yeah, thanks. Yeah, thanks for mentioning that. And that, this kernel arose just from the fact that we were doing gradient descent originally, right? So like, what determines maybe just to expand on that a little bit, the evolution of the parameters was coming just from df d theta, and so that kind of gave rise to this, and so that's why it's still there. I feel like I perhaps confused people.
Should we be surprised that Bayesian inference sort of over all the parameters of the whole network gives you the same thing as just training the last layer? Like it sort of seems, intuitively the Bayesian thing seems like it's really involving the whole network. But somehow, does this mean that sort of like, in an entropic sense, sort of all the stress is falling on the last layer?
Yeah, I guess I kind of, there are some details there that you would want to prove rigorously that I kind of didn't do. Like, because first we kind of mapped it over to a G, so I don't want to make claims about the posterior in like weight space and how it converges kind of to these sorts of things, because we didn't really prove that. What we kind of did was we mapped it to a GP, so we took the limit first and then we did Bayesian inference. And like, be fully rigorous or fully comfortable, I feel like you want to close that other loop. And other people have actually worked on this topic, but I don't know that I can kind of speak to that.
That was
Does that
also
help?
there's a time question. If you do Bayesian inference
On
all the parameters.
all the parameters, you get just the last layer. Yeah, like I guess I would just feel more comfortable when you have a fully mathematically rigorous proof. Maybe I don't claim, I just mean to compare the formulas, that's all. So that's one answer we got yesterday, this is a different answer. There's some similarity between them. But this one involves two kernels. Maybe
Is there any sort of like mixed kernel such that this is the posterior distribution of the GP with this like hybrid kernel?
I don't know that that's, I think people have tried to answer that question. I don't know of any answers to that question.
Okay. I didn't understand.
Is there, I think the question was like, is there a GP for which if you did Bayesian inference, actually, was that the question?
Yeah.
That you would get this thing. So like not, this formula with theta naught and k in there.
As a variance.
As the variance, yeah. Like this is the final distribution you would get, but you want to know how, what prior should you assume, so that you would get these sorts of formulas rather than the one that we got.
But then maybe I misunderstood because I thought this was rather than the variance was the correction in deviations, like the second order term. But not as a variance, but
No. This is all infinite width limit. No corrections yet to kernels or dynamics. This was all just solving infinite width limit. It's the NTK solution, but just The sigma?
Yeah.
This is just the so I'm trying to make a prediction. What is the distribution of f, the function, on some batch of test points, chi t?
With respect to initialization.
With respect to initialization, which are these f naughts, which are GPs from yesterday. But we did gradient descent dynamics, so we got other stuff. Okay. Sorry if that was so, but anyway,
Can you remind us what is the K again? Like, how is K and so I get?
oh, how does K enter? So
How
it
is
just
it even defined?
it was from yesterday, but f sub 0 is is a GP with mean and covariance A. There's a layer L in there, but this is just the distribution of the output required on the functions that we got yesterday. And that comes in because here, this is the randomness, the source of randomness. So if I want to take like, if I want to compute expectation of this thing, I get the mean of the GP and so on, but the distribution of this of the GP carries over to the distribution of this output.
I see, and it doesn't attack.
It doesn't.
Because in a sense, the sigma, I mean, we are not used to, I'm just trying to think back about the kind of kernel regression formulation of this, in which we don't have sigma. We would just have the mu.
That's right.
And
Yeah.
then the k would not come out at all.
That's right.
And we would just have the
That's right.
first equation is basically regression without regularization with the kernel theta 0.
Yeah, that's right.
That's
Yeah.
all it is. And then, okay, the equation that looks, at least to me, a bit kind of unfamiliar is this one. But what this actually is the variance with respect to the initialization. Okay, why not? Okay.
Yeah,
Just,
exactly.
like,
Which
used to think about that.
Which you could kill if you wanted by just setting it to 0. If you initialize the entire network to 0, then this doesn't come up. This is just kind of, this result is just for a fixed initialization, so like it's quenched. And then if I want to think about the distribution over such an ensemble of such networks.
Okay, so there is no reason in a sense for this to be in any way related to the GP sigma, because this is just a different thing. The GP
That's right.
assumes a distribution, whereas here I kind of postulate a distribution on the initialization.
Well, I don't, that's true, but I don't
For any
postulate.
initialization I express the...
That's true, but there's only one initialization that's relevant here, because because we worked in an infinite width limit, and all of this was kind of, the NTK result was all derived from a particular scaling,
Okay.
and so that GP also kind of necessarily pops out of that. So
Right, but
if
if
you,
the GP in essence is not a gradient descent, I just don't have any dependence on
That's right.
initialization because there is no initialization. It's just okay.
it's the ensemble of such networks, and then I do Bayesian inference with that, which was that other formula, and also from yesterday. Yeah, so this is, if you want to just treat it as kernel ridge regression and not track the variance exactly right, you can just look at that term.
Then, sorry, just to make another comment, then it's not fair to say that gradient descent converges to the kernel regression problem, because the solution has a variance, so I'm not expecting the predictor itself to be exactly the one of kernel regression, but only phi average over initialization, right?
No, the predictor does not depend on the initialization.
But I understood that mu is the average and sigma is the variance of the predictor.
The predictor does technically have some, if I don't average, you're right, it has some knowledge of F0. I think is what you're saying. Whereas I would lose all memory of that if I were just, or if I set it to 0, then I also have no memory of it. If I force my network just to be initialized to 0. I think I agree with what you were saying though. So like you know, what I wrote here was that ft of x is really the sum of two terms.
Oh, the predictor is the sum.
When I'm just fixing an initialization and running it forward. And also this is all gradient flow. Just to, gradient descent looks a bit different. But yeah, and then I just split it into two terms to isolate the part that one has some randomness in it and the part that is independent of the randomness. Yeah, okay, thanks for that comment.
No, it was a general question because I always thought before that it will convert, like the predictor itself will convert to. But yeah.
So you're saying that in order to evaluate f, I actually need the sigma? No. Sorry.
Not to evaluate f, so you give me a network, I could just evaluate f, but if I want to now, what I'm doing is, you know, taking the ensemble, you know, what is the distribution of ft on some x star, some test point, but here it's like a batch of test points, where this is kind of like, this distributional nature comes from just the initial weights, or the initialization. So this is a normal distribution. You know, if I okay, in the, I think I have like 10 minutes, 5 minutes. Maybe I want to, guess we won't get to too much of the details of a proof. So I wanted to just highlight, you know, the original NTK result. It's a really beautiful paper. They kind of do the analysis in function space, and they do it for continuous time and square loss, and you can solve it exactly in all this. I just want to highlight a couple things because we'll relate it. We'll come back to it in lecture 3, and this is stuff that appeared in later papers. So there's, you know, many papers on this topic, and I'll give full list of references. But let me quote something from a later paper that looks a bit more at the case of, that talks about the linear model equivalence, but also looks at the case of gradient descent a bit more.
Can I have one more question? Sorry. If I actually added a regularization to all that, then would I just drop the dependence on the initialization? Is that what would happen?
Well, one thing is with the depends on the regularization.
Just weight regularization.
But it may, so if this is like, you know, an L2 norm on the weights, it may break the NTK result. So I think, I don't want to quote like what results are out there, but like if you imagine that I put, you know, L2 on the weights and it's about the origin. So it's not about the initial point theta naught. So probably that breaks this aspect of the fact that like the weights move by within some wall depending on the parameterization. Yeah, so you'd have, not every regularizer would work if you did that.
Okay, but if I somehow still did that, that would destroy the dependence on the initialization. Okay, but it would not be the limit, okay, I see what you're saying.
You also wouldn't be in the NTK regime if you did that. Like your NTK
Yeah,
would
you
change
would not be
even
in
in the
the
NTK
NTK.
parameterization. You would have to like deal with that.
Okay, so let me talk about some assumptions that you need for kind of a more general proof of NTK. One thing is that it holds with gradient descent up to some maximum learning rate. And that's something that I want to talk about in lecture 3. So, you know, I'm not going to write out the full theorem, but run, you know, gradient descent with learning rate eta less than eta critical, where eta critical is like this. So I take theta, or theta naught, it's like the theta at initialization, and I compute the maximum and eigenvalue kind of govern some critical learning rate. So for us, mostly like for realistic problems or problems that I mostly think about, this is small. So it's, approximately this. But this is an important condition. So like if you're taking a finite width network and you're above this learning rate and you're making the network wider, you don't approach NTK dynamics. So we'll talk about that tomorrow. Okay, so if you have these conditions and a bunch of other, and assume, as I think Julia mentioned yesterday, something like this, then you have some equivalence with linear models. So the actual function as a function of time compared to some linearized version of it. This is some kind of statement about the equivalence, again, after Jacob et al. So I didn't quote their example to try to show something a bit more general in terms of like gradient descent and critical learning rates. The types of conditions you're getting are that the deviation between the actual neural network function and the linearized version of it goes to 0 over all time. Note that the total change in the weights is something that is order 1 when you sum over all of them. So like per coordinate, it's suppressed, as we talked about. And then the change in the NTK, where this theta hat is a finite size version, is also vanishing. Lost in my sea of notes. Okay, there's one thing that I now related to this that I want to emphasize, which is parameterization. Which is the following. So just keep in the back of your mind that there are, of course, multiple parameterizations. There's the mean field type of kind of work where you're not dealing with any 1 over root n's, but you have a different factor altogether. And then in the infinite width limit, you get feature learning, not this equivalence to kernels. So that's different. But let me just compare this, the one that was used originally in the Jacob et al. Paper, and what is sort of, for many years kind of been the standard parameterization in some library you might actually run for neural networks. And the differences appears in how you parameterize these things. So this is the type of recursion we were dealing with yesterday. Excuse me. Okay, for the GP, and then we have priors like this, and we put the 1 over n scaling in the variance of the weights. Okay, now over here, we have something like this. I've done two things here. One is that I've pulled out sigma b and sigma w, but that's not important. But I just did that to make contact, with what they do in this paper. What is different is this 1 over root n that's explicitly here. Now, for the point of view of the forward dynamics or the equivalence to the GP, it doesn't matter because we go to, we have central limit theorem in both cases. We can calculate the covariance function. In both cases, it turns out to be the same thing. But where it does start to change things is in dynamics. So imagine that you start to take gradients of this, of the loss with respect to the weights. They differ in this 1 over root n factor versus not, because now the prior doesn't help you anymore, or it doesn't balance out. So in general, these two dynamics are different, and you can actually show, and maybe I'll have this in the notes, that for different arbitrary architectures, you need to have more degrees of freedom on one side of this to actually map one type of dynamics to the other. So like, given an initial point in parameter space, if I take one step of gradient descent with this versus one step of gradient descent with this, I may need layer-wise learning rates to kind of make those two dynamics equivalent. And so you might start to wonder, if I'm studying this problem in the infinite width limit, is that related actually to this other problem, which is maybe perhaps the thing that you would run if you were doing kind of standard package neural networks, this type of thing. In the case where all the layer sizes are the same, kind of it reduces a bit further, but they're still different. One way that they're different is in the way that you need to scale learning rates. So in standard parameterization, it's natural to take a learning rate which scales as 1 over n, where eta naught is something that's order 1. Eta naught, in reference to what I wrote before, is this sort of thing. So if theta is like a nicely normalized, properly normalized NTK, these eigenvalues are properly normalized. This is order 1, and this is the sort of thing that you would plug in for eta naught. This 1 over n thing is kind of important for the stability. If you imagine, if I compute the NTK in this parameterization, what I get is like a sum over n terms. And I'm not helped, like imagine just taking gradients with respect to this thing. And so, the top eigen, the entire spectrum of that thing kind of scales with n. And so to stabilize it, I need a 1 over n here. Whereas in NTK parameterization, it's more natural to just have an order 1 quantity. So this is one example of like a nice, kind of just trivially, a nice parameterization in the sense that the range of hyperparameters you're sweeping over as you change the model size also isn't changing.
In the standard parameterization, is that n with varying different layers, or is this sort of like
it is. So it depends what you want. Probably if all the layers are growing, it's enough to just have the max or the min of them. If they're all growing kind of at similar rates, probably it's enough to just factor out kind of one of the n's. If you want to map between these two different parameterizations in general, you need kind of layer-dependent learning rates, and that's where like different layer n's can come into play. How much time do I have left? Okay. Then maybe I won't do anything else kind of here. I'll just mention that, I don't know if anybody wants to see me write it, but the statements for these types of theorems then change if you're running, in standard parameterization. So this thing is not, doesn't scale in this particular way. You can still show that the there is some NTK kernel where you have to like normalize it properly. So in standard parameterization, you know, the equivalent thing is to put a 1 over n on all the derivatives explicitly. If you want to kind of relate it to these other results. But the size of the ball that you're working in for the proof and the way that the gradients kind of scale also changes by this factor. So you kind of have to, so just keep that maybe in the back of your mind, depending on, you know, this is very particular to NTK parameterization, what I wrote, how much the weights change and so on. Any questions? I think I'll just end there, I guess. It's a natural ending point. And so tomorrow, what we're going to do is not talk about NTK anymore, but go back to kind of the time derivative equations I had for theta and so on, and try to kind of motivate some sort of like function hierarchy, function space hierarchy, where we have lots of dynamical variables in function space kind of marginalizing over the parameters, and then we're going to do something kind of more physics style where we're going to attempt to solve it to leading order.
Maybe I had a question. In all this, why do we concentrate so much on the square laws?
Because it's easier, well, because I think it's, a lot of the proofs depend on that, so this fast rate of convergence, you know, and the fact that you can stay in this is my understanding of it. I think one of the reasons is the fact that you can stay in this kind of ball of a certain size, and you get this very fast convergence. And also just, I tend to emphasize it because you get these analytic formulas out of it, which physicists, you know, like you like to do calculations with that.
Yeah, that's
but
basically
like,
my question.
I think
you
that's
say
the main.
With that logistic loss, is it that we would just lose this explicit kind of solution of the dynamics, but otherwise it would be essentially the same, or is there something else that would change?
You're asking, is it valid with these other losses, or?
Yeah.
Yeah, I think, so I think there are probably more experts in the audience who could answer that better than I would. And maybe not to mention this, but I would imagine that it depends on, for example, for cross entropy, I don't know what the latest kind of literature result is, but you would imagine that it, if you run it for infinite time, it's not going to work. Just because, at least, or you're going to have to adjust it in some way, just because the change in the weight scale is also running to infinity, and so the equivalence to a linear model, you know, probably breaks down unless you can show higher order terms are suppressed. So maybe there's a version of it where you run it just to finite time, you know, to within error epsilon, and then you take width to infinity, and you still manage to kind of suppress it. That's what I would guess exists, but I'm not, I think, the most up-to-date on what's been proven. Any other questions?
Okay.